part of the BocaPhysics mini course on nuclear physics. In today's lecture, I'm going to discuss nuclear reactions, including the nuclear processes that occur inside of a fission reactor and also processes that would occur inside of a fusion reactor. Now, last time around, in the previous lecture, we discussed alpha and beta decay. So I kind of want to segue over from that lecture in today's lecture. So I'm going to begin with natural radiation series. Okay? Now, remember, in alpha decay, an unstable nucleus emits an alpha particle, which is basically helium nucleus, and a daughter nucleus that has 4 fewer nucleons, 2 fewer protons, and 2 fewer neutrons. We also discussed beta decay, and for purposes of today's lecture, I'm just going to mention beta minus decay. That's where you have an unstable nucleus emitting an electron, and also an electron antineutrino, and the daughter nucleus will have 1 more proton and 1 fewer neutron. So the total mass number in this case stays the same. So basically, the daughter nucleus is an isobar of the parent nucleus. Okay, so if we, or if you take a look at the heavier elements, 3 of those elements, or 3 of those species will stand out for their very long half-lives. And that would be uranium-238, uranium-235, and thorium-232. Uranium-238 has a half-life of about 4.5 billion years. Uranium-235 has a half-life of 700 million years. And thorium-232 has a half-life of about 14 billion years. Okay, so these nuclides obviously are unstable, so they're going to emit particles, and in fact each of them begins by emitting an alpha particle. Well, their descendants are also going to be radioactive, and they'll be emitting alpha particles or beta particles, as the case may be. But notice here that the mass number can only change by 4 for each decay. At most. So for any of these decays, alpha or beta decay, the mass number is going to change by 4 in the case of alpha decay, or not at all in the case of beta decay. So what I'm going to show you now is how these natural radiation series progress. We'll start out with uranium-238, in one case uranium-235, in the second case, and thorium-232. Now there are 4 potential series because mass number could be start with the A being equal to 4 times some integer. Thorium plus 1, thorium plus 2, and thorium plus 3. So there are 4 potential natural radiation series, and notice I just mentioned 3 of them. So I'll get to the 4th one after we go over the figures. And I do want to emphasize, though, that these are not the only processes these species or any of their descendants undergo. There are such things as spontaneous fission or the emission of a heavier particle that can occur as well. But we're just focusing on alpha beta decay because those are the most likely decays that can occur. Let's begin with the 4n plus 2 series, which originates with uranium-238. This is called the Uranium Series. The colors again represent the order of the half-life from billions of years down to a tiny fraction of a second. Uranium-238 has a half-life of 4.47 billion years and most likely undergoes alpha decay, but there is a small probability of spontaneous fission. The daughter nucleus will have 4 fewer nucleons, 2 fewer protons, and 2 fewer neutrons, which in this case is thorium-234. Thorium-234 has a much shorter half-life of about 24 days, and it undergoes beta decay, resulting in a daughter nucleus that has 1 more proton and 1 less neutron. And that'll be protactinium-234, and the series continues. You'll notice that the nuclide polonium-218, there's a branch. This means that both decays are energetically possible and do happen. The black line indicates a more probable decay. The blue line indicates a less probable decay. Ultimately, the uranium series ends in lead-206, one of the 3 stable isotopes of lead. Next, let's consider the actinium series, which originates with uranium-235. This corresponds to A is equal to 4n plus 3. The half-life of uranium-235 is over 700 million years, and uranium-235 most likely undergoes alpha decay. Its daughter nucleus is thorium-231, which undergoes beta decay, and its daughter nucleus is protactinium-231, and so on. Notice once again there are branches at actinium-227, francium-223, astatine-219, and so on. This indicates that both beta decay and alpha decay can occur. The actinium series ends in lead-207, another stable isotope of lead. Finally, let's consider the thorium series, which originates with thorium-232. This corresponds to A is equal to 4n. Thorium-232 has a half-life of 14 billion years. Notice that the branch at bismuth-212, both lines are black, indicating that both decays are likely to occur. Specifically, the alpha decay has a 36% probability of occurring, and the beta decay has a 64% probability of occurring. This series ends at lead-208, another stable isotope of lead. And the one series that was missing corresponds to 4n plus 1. If you consult a table of nuclear data, you'd see that what appears to be the genesis of this series would be neptunium-237. However, its half-life is only about 2 million years. Now, if we assume that all 4 of these were formed at the same time ago, billions of years ago, it's easy to see how neptunium-237 would have decayed away, as would its descendants. So this is why neptunium-237 is not included as part of the as one of the natural radiation series. I want you to keep alpha decay in mind for what's coming up next. First, we're going to answer the question, where are nuclear reactions rare on Earth? And I mean rare in comparison. Chemical reactions occur all the time. And are ubiquitous. Well, there are 2 reasons for this. Number 1 has to do with the size of the nucleus. Nuclear radii are the order of femtometers. Remember, a femtometer is equal to 10 to the minus 15th meters. That's in contrast to atomic radii, which are on the order of angstroms, which is 10 to the minus 10th meters. So, for one thing, nuclear radii are much smaller. Now, there are occasions when nuclei can behave as if they have, as if they're as big as an atom, and that's getting into a little bit about cross sections, which we'll also discuss a little bit later on in this lecture. But anyway, that's one of the reasons why nuclear reactions are, in comparison, rare on Earth. Number 2 has to do with Coulombic repulsion. So you got to overcome this great repulsive force in order for nuclei to get close enough together. So chemical reactions are in the order of electron volts. Nuclear reactions, in contrast, are in the order of mega-electron volts. So that's why nuclear reactions are, in comparison, rare. Now, they're not rare in the universe. Fusion reactions go on all the time. In that great fusion reactor in the sky, the sun, and we'll talk a little bit about those processes later on in this lecture. But most people aren't aware that there were actually natural fission reactors here on Earth in operation something like a couple of billion years ago. So that makes for a really interesting story, and I'll get to that later on in the lecture as well. But for now, I want to talk about the very first nuclear reaction that was observed, and that involved an alpha particle. So let's get to that next. Ernest Rutherford observed the first nuclear reaction. He bombarded nitrogen-14 with alpha particles. One of the products of that reaction was oxygen-17. Now, this other particle had the property that, even though it had comparable energy to helium nuclei, its range was much further. And in fact, the range of this particle was similar to that of hydrogen nuclei. So from what he concluded from that was that a hydrogen nucleus must have been produced in this reaction. As it turns out, this is one of a series of similar reactions where an alpha particle bombards a target and a proton is produced, as well as a daughter nucleus. So generally speaking, this is written have our helium nucleus, helium-4, that bombards a target that has mass number A, atomic number Z, and a proton, or hydrogen nucleus is produced, and a daughter nucleus that has mass number A plus 3 and atomic number Z plus 1. Now I mentioned that this is one of a series, so another similar reaction is an alpha particle bombarding boron, in which case, once again, a proton is produced and carbon-13. It's interesting to explore the energetics of these kinds of nuclear reactions, or actually any kind of nuclear reaction, and the reaction energy is defined as the difference between the total initial masses and the total final masses. So if Q is greater than 0, what that means is that energy will be released. And if Q is less than 0, energy is absorbed. First reaction is often called exothermic or exoergic. The second reaction is termed endoergic or endothermic. Okay, so let's calculate the reaction energies for each of these reactions. And a little bit shorthand notation there, instead of writing out all these pluses and the arrow. You have the target nucleus, the kind of reaction, and the daughter nucleus. Total initial masses, that's going to be the sum of the helium-4 atom, that's 4.002603, and nitrogen-14, which is 14.003074, and then hydrogen atoms, 1.007825, And oxygen 17 is 16.999131. And it's times c squared, and of course we need to multiply this by the conversion factor of 931.5 mega electron volts over c squared over u. And I left off the u, let me just stick that in there. So the u's will cancel out, the c squareds will cancel out, and basically we're just multiplying this sum by 931.5 mega electron volts. And when you do the math, it's a result that reaction energy is minus 1.191 mega electron volts. So in this case, energy is going to be absorbed. That energy has to come from somewhere. And it's going to be provided by the kinetic energy of the initial particles. Well, now, in this reaction, and actually any reaction that we consider in this mini course, we're going to assume that the target nucleus is at rest. So the kinetic energy will just be provided by the alpha particle. Now, if I consider the second reaction, involving boron 10 and producing a daughter nucleus, carbon 13. So once again, the mass of the helium atom is 4.002603. The mass of boron 10 is 10.012937, all of course in atomic mass units. And mass of the hydrogen atom is 1.007825, and mass of carbon 13 is 13.003355. So instead of writing all these U's in here, let me just say we're going to be multiplying this by 931.5 mega electron volts. In this case, the second case, 4.06 mega electron volts of energy will be released as a consequence of this nuclear reaction. So I mentioned this, this energy has to be provided by something, otherwise this reaction will not occur. Now, alpha particles are produced naturally, as we saw when looking at the natural radiation series, and they have sufficient energy for this process to occur. And I'm going to calculate, well, what's the threshold? How much kinetic energy does the alpha particle have to have in order for this reaction to go? And to do that, I need to appeal to conservation of momentum and conservation of energy. So let me go ahead and work out what that would be. For this case, and then of course, the reasoning can be applied to any reactions with similar conditions, okay? So I'm going to, fortunately, going to have to erase quite a lot of this. Now, granted, for the present, we are interested in this particular nuclear reaction, but I'm going to write the result a little bit more generally to that. So in this case, we have some incoming particle A that collides with the target nucleus. And as a consequence of the nuclear reaction, you have two products formed. You have the daughter nucleus and another particle B. We're interested in the threshold kinetic energy to make this reaction go. So basically, this is what is the minimum kinetic energy to make reaction go. going to assume that the target nucleus, X, is at rest. And that'll be a reasonable assumption for this particular example that we're working through, and then basically for any of the problems that we're working through in this mini course. I also have to make another assumption, and that is that the kinetic energies are a lot less than rest masses. In order to solve this problem, I'm going to make use of both conservation of energy and conservation of momentum. And conservation of energy tells you that the total amount of energy initially in the system is equal to the total amount of energy in the system after the reaction occurs. Conservation of momentum likewise tells you that the total momentum in the system before the nuclear reaction is equal to the total momentum in the system after the nuclear reaction. Now we've got two particles initially and two particles finally. So conservation of energy becomes EA plus EX is equal to EV plus EY. Now I'm going to break it apart into the rest mass contribution and also the kinetic energy contribution. And I'll denote kinetic energy by a capital letter K. And I will read this off. On the left-hand side, we have MAC squared plus KA plus MXC squared plus KX is equal to MBC squared plus KB plus MYC squared KY. Now let me read this off. This is MAC squared plus KA plus MXC squared plus KX is equal to MBC squared plus KB plus MYC squared plus KY. Now remember, we just defined the reaction energy equal to the total initial mass minus the total final mass times c squared. And in that case, this becomes MA plus MX minus MB minus MY c squared. So I'll be able to rewrite this expression. Conservation of energy then becomes Q is equal to KB plus KY minus KA minus KX. But we're interested in the minimum kinetic energy to make the reaction go, and furthermore, we're assuming that the target nucleus is at rest, so therefore KX is just going to be equal to 0. Now, applying conservation of momentum, and again, because the target nucleus is at rest, we can set that momentum contribution from the target nucleus equal to 0. Now, I'm going to solve for this, or rather, I'm going to eliminate all the y quantities in order to solve this problem. And I'm going to go ahead and take the dot product of this equation with itself. So on the left-hand side, I'll have py squared is equal to pa squared minus, or rather plus pb squared minus 2pa dot pb. Okay? Now, generally speaking, when you've got a target nucleus being struck by some other particle, the products are going to fly off in different directions. And I shouldn't say just different directions, but they're not going to just be going in the x direction, they're going to be going in the y direction too. But remember, we're interested in the minimum amount of kinetic energy to make this reaction go. So we don't want to waste any energy or momentum, waste in quotation marks, on particles going off in the y direction. So in this case, we're not going to make the assumption that theta b is equal to 0. So basically, we're assuming that all the motion takes place in the x direction, either to the right or to the left. And that's going to simplify things quite a lot. So I'm going to rewrite this term, or actually every term, in terms of the kinetic energy. Remember, kinetic energy is just equal to p squared over 2m. So therefore, on the left-hand side, this becomes 2my ky. This becomes 2ma ka plus 2mb kb. And then last but not least, we have minus 4. And now it's going to be square root of ma mb ka kb. Okay? These are our two equations. And I'm going to solve for, ultimately, B quantities in terms of A. So I'm going to go ahead and multiply this first equation by my. And have ky on one side. Off my ky is equal to m1 all times q plus ka minus kb. And then we also have, again, this is from conservation of energy, this is from conservation of momentum. My ky is equal to ma ka plus mb kb minus 2 square root of ma mb ka kb. So I just set the right sides equal to each other. so I've just written out, separated everything with, that's a factor of KB, everything that's a factor of square root of KB, and the remaining terms. So again, we have 0 is equal to MB plus MY times KB, minus 2 square root of MA, MB, KA, and square root of KB, plus MA, KA, minus MY, KA, minus MY cubed, the reaction energy. Okay, so this is just a quadratic equation, and it's quadratic in terms of square root of KB. So therefore, I can solve for the square root of KB. Things are getting really scrunched up, so let me just read this off. In the denominator, we have 2 times MB plus MY. In the numerator, we have 2 times square root of MA and B, KA, plus or minus square root of 4 times MA and B, KA, minus 4 times MB plus MY. And this is probably the hardest to read, last parentheses. MAKA minus MYKA minus MYQ. Okay? So that's solving for the kinetic energy of particle B in terms of the bombarding particle A. So say it again, we're interested in minimum kinetic energy to make this reaction go. Well, that's going to occur when this quantity under the radical sign is equal to 0. Just enough kinetic energy for this to be larger than 0, okay? First, I'm going to have to erase some of this. So we have MA, MB, KA, and this is minus MB plus MY times looking for what kinetic energy causes this quantity under the radical to be equal to 0. I'm going to multiply everything out. So these first two terms drop out. MA, MB, KA, and there's minus MA, MB, KA. Then all the remaining terms have a factor of MY in common, so those cancel out. then we're left with threshold kinetic energy. The minimum kinetic energy to make this reaction go is equal to minus Q view reaction energy times MB plus MY in the numerator divided by MB plus MY minus MA in the denominator. So that's the minimum amount of energy that this particle needs to have in order for this reaction to occur. Okay? Now, we were looking at the collision of an alpha particle and a nitrogen-14 nucleus, and we calculated Q to be, in that case, minus (1.192 megaelectron volts. So let's go ahead and plug in the numbers again. Remember, this was for the nuclear reaction. An alpha particle bombards nitrogen-14, and as a consequence of that, hydrogen and oxygen-17 are formed. So plugging in these numbers, in this case, the mass of hydrogen is going to be 1.007825. Mass of oxygen 16. Is 16.999131. And that's all divided by all divided by 1.007825 plus 16.999131 minus 4.002603, which is the mass of helium-4 atom. That's equal to 1.53 megaelectron volts of energy, the minimum amount of kinetic energy that the alpha particle has to have in order for this reaction to go. Now, the alpha particles that were used and still are used in these kinds of reactions are from natural sources, and typically are the products, or I should say the consequence of alpha decay. And typically these alpha particles have energies on the order of 5 megaelectron volts. So there's certainly enough kinetic energy in order for this reaction to go using naturally available sources. And it's the case that not just protons are formed, or hydrogen nuclei, are formed if you have an alpha particle bombarding a nucleus. Other particles can be formed as well. So let's take a look at the discovery of the neutron. It was the husband and wife team of the Joliot-Curies who first investigated this particular nuclear reaction. They bombarded a beryllium-9 target with alpha particles, and what they observed is that an isotope of carbon was produced, and they also observed that there was another particle that carried no electric charge. They made the very plausible assumption that this was a gamma particle, because gamma particles, photons were known at that time, and photons don't carry electric charge. That would have meant that this was carbon-13. So let's take a look at their experimental setup. There were alpha particles. Here's your beryllium target. And here's your mystery particle. Which was allowed to bombard a block of wax or block of paraffin. And what they observed was is that protons were knocked out. With momentum 100 megaelectron volts over C. So let's investigate whether this assumption is actually a valid one. We're going to first calculate what kind of energy this photon would have if this were the reaction that occurred. So we're going to suppose that photons were produced. And then we want to ask and answer the question, what energy would they have? And to figure that out, I'm going to look at the masses of each of these. I mean, the mass of the helium atom, or helium nucleus, but remember we always work in atomic masses. That's going to be 4.002603. The mass of beryllium-9 is 9.012183. And the mass of carbon-13 is 13.003354. And those are all in atomic mass units, so I need to convert to megaelectron volts. And that really amounts to multiplying by 931.5 megaelectron volts. Now, these alpha particles are produced with an energy of 5 megaelectron volts. So let's do the math. And that means the photon would have energy 15.6 megaelectron volts. Okay? So that's how much energy this particle would have. We're looking at this particular part of the experiment now. So I'm going to apply conservation of momentum and conservation of energy to figure out, are these results consistent? So remember, conservation of energy is total momentum before the reaction has to be equal to the total momentum after the reaction. And the total energy before the reaction has to be equal to the total energy after the reaction. So initially, we've got our gamma particle, our photon, and we've got the proton. And afterwards, we've got photon and the proton. Okay? For the energy, we've got the, remember for massless particles, E is equal to PC, so energy is just equal to momentum times the speed of light. So for the photon, that contribution is going to be, well, let me just write this out term by term first. So this is photon, proton, and photon, and proton. So that's EI gamma plus EI proton plus EF gamma plus EF proton. This term is going to be P gamma times the speed of light. This contribution You've got a kinetic energy term, you've also got the rest mass contribution as well. Kinetic energy contribution is going to be 0 because we're assuming that the proton's initially at rest. So this will just be mp c squared. Over on the right-hand side, the energy of the proton is just going to be its momentum times the speed of light. And in the final term, we have a kinetic energy contribution because now the proton has been set into motion. So that first term is going to be p fp squared over 2mp plus the rest mass contribution. So there's a rest mass contribution from the proton on both sides that just drops out. Now up here, the momentum of the proton is initially 0, so that term drops out. And remember, these are vector quantities, so imagine our gamma particle comes in from the right, and it's going to have opposite momentum upon colliding with the proton. So here are 2 equations, and we have 2 unknowns here. 2 unknowns, of course, are the momentum of the gamma particle, or the gamma ray. Okay, so if I multiply through both sides by c, in the second equation, and rewrite the first equation, energy equation on top, and add these up. So let me just read this off. This is pi gamma times c is equal to pf gamma times c plus p fp squared over 2mp. Again, that's this is from the energy equation. The second one's from the momentum equation, which I just multiplied through by c. So this is pi gamma c is equal to minus pf gamma c plus pfp c. You add these 2 up, is f gamma terms drop out, and we'll wind up with 2 pi gamma c is equal to pfp squared over 2mp plus pfp times c. Well, let me just read this off again. This is 2 pi gamma c is equal to pfp squared over 2mp plus pfp times c. Now I want to keep everything in units of mega electron volts over c. So we first divide through everything by a factor of 2c. And in this first term, I'm going to divide and multiply through by c squared. Okay, and that should have a 2 over there as well. Okay, so this first term is going to read 1 over c, pfpc, both terms squared, all over 4mp c squared plus pfp over 2. And unfortunately, once again, I'm running out of space here, but I'll leave this 1 over c here. So in the numerator, we have 100 mega electron volts. Remember, the momentum of the proton after the being knocked out of the paraffin is equal to 100 mega electron volts over c, and we're just multiplying by c. So in the denominator, and again, I'm really not leaving enough room here, the mass rest energy of the proton is 938.3 mega electron volts. And this last term is 100 mega electron volts over C divided by 2. And that leaves me with 50. And when you do the math, what you'll find is that the gamma particle would initially had to have had momentum 53 mega electron volts over C. That's a great discrepancy from the energy that it could possibly have. I mean, remember, if we wanted to figure out the energy that the gamma particle had, we just multiply this by C, which would be 53 mega electron volts. So where does that excess energy come from in order for this reaction to occur? So it was James Chadwick who realized that there was a big problem if this particle were a photon in this particular case. So James Chadwick said it was not a gamma particle at all, but a new particle called the neutron, which has mass that's roughly equal to the proton, and carbon-12 would be produced as a consequence of the reaction. Now, this is a good method for producing neutrons. Basically, you take an alpha emitter, like radium-226, and has a half-life of about 1,600 years. So if you've got radium and beryllium, presto, you've got a source of neutrons. This works very well. The one drawback is that gamma particles are produced also in this process, very powerful gamma particles. So some people instead will use polonium-209, okay? And by the way, this is not the only kind of reaction that occurs. There are other processes where you have an alpha particle colliding with a nucleus and producing a neutron. So these are called alpha N type reactions. Okay, so let's consider next what happens if you bombard a nucleus with a gamma particle. You can also cause nuclei to disintegrate by bombarding them with gamma radiation. So let's take it for instance here. Let's suppose you've got a target of beryllium-9, and you bombard it with gamma radiation. What's going to be produced? Well, two things that you know are conserved in any kind of nuclear reaction. Nuclear number must be conserved, and the electric charge must be conserved as well. So therefore, the daughter nucleus in this case is going to be beryllium-8 plus a neutron. So the question is, what's the minimum energy necessary for this reaction to occur? Well, actually, before I get to this particular nuclear reaction, let me take a look at a simpler one, or more fundamental if you prefer. Let's suppose you bombard deuterium with gamma radiation. What energy is necessary for that reaction to occur? Remember, a deuteron is just composed of a proton and a neutron. So basically, this is the amount of energy that it takes to rip that nucleus apart. So we have a hydrogen nucleus and a neutron. And let's do the math on this. So the mass of hydrogen is 1.007825. Mass of the neutron is 1.008665, and the mass of deuteron is 1.014102, and that's, again, all of these are in atomic mass units, and remember we need to multiply by 931.5 mega electron volts to convert this from atomic mass units over to mega electron volts. And if you want to be a stickler about putting all the units in, these all have units, atomic mass units, and the conversion factor is going to look like this: 931.5 mega electron volts over c squared is equal to 1u, and of course then everything's multiplied by c squared. So c squares cancel out, u's cancel out. It's basically the same thing as multiplying by 931.5. And you do the math, you'll wind up with 2.22 mega electron volts. Now, if that number sounds vaguely familiar to you, then you must have been looking into or been watching a video on binding energies. And if you watch the first video in this mini course, we talked about the binding energy of deuterium, and that was 2.2 mega electron volts. So, in fact, that's the amount of energy necessary, minimum energy necessary, to rip the deuteron apart. Okay, so now let's turn our attention back to beryllium-9, and I want to figure out, again, what's the minimum energy for this reaction to occur. So beryllium-8 has a mass of 8.005305. Mass of the neutron is 1.008665. And finally, the mass of beryllium-9 is 9.012183. Again, multiplying by conversion factor, and the upshot of that is we're multiplying by 931.5 mega electron volts. You need to do the math. And you'll wind up with 1.66 mega electron volts. Now that's clearly not the binding energy of either beryllium-9 or beryllium-8. Essentially what it is, it's the binding energy or the separation energy required to rip a neutron apart from beryllium-9. So, for comparison, let's look at the binding energies of both beryllium-9 and beryllium-8. And remember, the way you calculate the binding energy is that is the number, atomic number of protons times mass of hydrogen plus number of neutrons times mass of neutrons minus the mass of the atom in question. So in the case of beryllium-9, and again, these are all in atomic mass units times c squared. But again, the upshot of that is just multiplying by 931.5 mega electron volts. And that results in binding energy of 58.16 mega electron volts. I do the same thing for the unstable nucleus, beryllium-8. That's 4 times 1.007825 plus 4 1.008665 minus 8.005305 for the mass of beryllium-8 atom. And again, multiplying by 931.5 mega electron volts. And that gives me a value of 56.50 mega electron volts. And take the differences. It's going to be equal to 1.66 mega electron volts. Okay? So that's photodisintegration, and you would think of it as the amount of energy necessary to tear apart a neutron. Now, I don't want to leave you with the impression that neutrons are the only particles that might be emitted as a result of this disintegration. You can also have processes where protons are pulled out, or if you might even have a deuteron pulled out, or a triton pulled out. So a few examples of that. Let me write those on the board. Let's see, we've got a barred boron 10 with gamma radiation. That causes a deuteron to be pulled out, and you'll be left with beryllium-8. You can also bombard boron 11 with gamma radiation, and triton, tritium nucleus, will be pulled out, and you'll be left with beryllium-8 once again. So again, this is a reaction of the type gamma N. Second one is the type of the reaction gamma D, where little d represents deuteron, and this is of the type gamma T, where T represents a triton or a tritium nucleus. Photodisintegration is the inverse of radiative capture. So far, we've looked at nuclear reactions that involve naturally occurring radiation. We looked at alpha particles that bombarded a target and protons were emitted. We looked at alpha particles that bombarded a target, neutrons were emitted, and then we also looked at gamma radiation bombarding a target and neutrons were emitted. So again, bear in mind those are not the only kinds of reactions that are possible. With the development of accelerators, can accelerate charged particles and look at a whole new field of nuclear reactions. So let's take a look at the very first one, which involved firing 600 electron volt protons at a lithium-7 target. And as a consequence of this nuclear reaction, 2 alpha particles were produced. So let's consider how much kinetic energy was released as a consequence of this reaction. Once again, we want to look at the mass number, so we're really just calculating the reaction energy. this is the mass of the hydrogen nucleus, or rather hydrogen atom, 1.007825, plus the mass of lithium-7, 7.016003, minus, because we've got 2 alpha particles, 2 times 4.002603, and then again, we've got to convert that over to mega electron volts. And that gives me 17.35 mega electron volts of energy is released. Now, again, I don't want to leave you with the impression that if you bombard some target nucleus with protons, that automatically a helium or an alpha particle is going to be produced. So, consider what happens if you fire protons at the stable nuclide of beryllium-9. So yes, indeed, it is possible for this reaction to occur where an alpha particle is produced. So you'd have an alpha particle and lithium-6. However, it's also possible if you bombard a beryllium-9 nucleus, you'll have a deuteron produced, in which case beryllium-8 will be one of the products, okay? So both of these reactions can and do occur. They've both been observed. So it's definitely not the case that when you bombard a target nucleus with a proton that automatically an alpha particle is going to be produced. Okay, so far we've looked at reactions where the ingredients, if you will, involved either an alpha particle, or the initial ingredients involved an alpha particle, gamma radiation, or protons. Now I want to turn our attention to neutrons. What happens when you have a neutron reacting with the target nucleus? What's produced in that case? And so now it becomes important to distinguish between slow neutrons and fast neutrons. So let's get to that next.